thought we'd start with a little puzzle I'm trying to solve. Maybe you can help me with the puzzle. Okay, let me make it a little less volume. Thanks. I don't need to echo that much. All right, so here's the puzzle. I thought this is a pretty interesting one, and it may be related to what we're going to do. Okay, so the question is, what's the next number in the sequence? 0, 1, 2. Any ideas? 4. 3. Any other suggestions? 1. Okay, no one has said the same number twice, so we have no consensus at all. We have 0, 1, 4, 3, 2, 5. 42, that's a good one. 1 over E would be a good guess. Okay. Any other suggestions? 1/2, 1/10. Okay. Well, I don't want to get a reason for each of those. Is there any majority opinion on this? 3. 3. Why did you say 3? Integers. Okay, 0 is an integer. Why 3? Yeah. It's a value, but values that the Poisson could take. Okay, but I don't have to list them in order though. I could have listed them out of order. All right. Well, okay. A lot of you seem to like the number 3, but I haven't yet heard a good reason why. I'm kind of interested. It's an arithmetic sequence. I hadn't noticed that. So I guess you're pointing out that it's an arithmetic. Hey, that's pretty cool. So you go from here, add 1, add 1, add. That's what arithmetic sequence. Okay, that might have been what the puzzle writer had in mind. I've been trying to solve this for the last couple of days. I got stuck. The best I hadn't thought of 3 yet. The best answer I thought of so far was 720 factorial. So we can debate a little bit. You know, is that more correct, or is 3 more correct? Anyone? Assuming it does go this way, anyone want to guess the next term? 3? Okay. All right. Yeah, I think you got it. All right. So all right. Let me tell you why am I talking about this sequence? Well, it's partly just like I always really. I love puzzles since the time I was little, but I hated this kind of puzzle because there never seems to be a principle for coming up with an answer. You can make up I make up one thing, and the answer is supposed to be something else. Well, what's the measure of what's a better, right? I mean, you need some measure of maybe the simplest answer, but will 2 people always agree on what's simpler? No, right? You need some complexity measure or something to actually make that into a valid, well-defined problem. So, in a sense, this is just as good an answer as 3. Some of you had in mind an arithmetic sequence. That's a good suggestion. But I was thinking of 0. Well, 0 is 0. 1 factorial, 2 factorial, factorial, 3 factorial, 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 4 factorial, 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 factorial. Which one of you just suggested it, and so on. That's 0 with no factorials, 1 with 1 factorial, 2 with 2 factorials, etc. Okay, and probably should put parentheses, but that's because this double factorial is also used to mean the skip factorial, where you go down by 2 numbers each time. But anyway, that means that's doing 3 factorial, 4 factorial, etc. All right, so well, I mean that's what one interpretation could be. So the general question is, if we have a sequence of numbers, how do we extend it? Okay, and I was thinking of this example because I was thinking about factorials and how I want to explain extending factorials. So, like, if you ever wondered what's pi factorial, we're going to talk about questions like that. If you didn't ever wonder what pi factorial is, that's okay. You'll see other uses for this kind of thing. So the question is, if you plotted, what does the factorial function look like? Well, 0 factorial is 1, that's 0. 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, 5 factorial is 120, 6 factorial is 720. Can't draw it anymore, right? It goes, way, it starts out pretty small and then it grows extremely fast. Very, very beautiful formula that gives you the approximations for factorial is called Stirling's formula, which if you haven't seen before, everyone should know this formula. It's both beautiful and useful. It says that n factorial is approximately square root of 2 pi n times n over e to the n. This is actually an extremely good approximation. Even if you try this out on a calculator where like n is like 12 or 20, it's actually very, very good. Not only that, but this approximation is so good that if you take the ratio of this divided by this, it will converge to 1 as n goes to infinity. So that gives you some, that's just a cool looking formula. By the way, we can prove this using probability, and I'm not going to do that today, but I might do that at some point. We can give this a probability interpretation by thinking about Poissons. But anyway, this gives us some sense of how fast does a factorial grow. This square root thing is not so important. The main thing that's driving it is this n over e to the n. So you basically have this n to the n behavior. It's discounted by e to the n, but n is, if you're letting n go to infinity, that's dominating over the e. So anyway, that's Stirling's formula. So that gives us a sense of how does this thing grow. But now my question is, how would you connect the dots? That is, if you want to, this function was only defined on non-negative integers, and if we wanted to interpolate, well, there's like many ways you could like draw, some function that connects those dots. Infinitely many ways to do it. The question is whether there's some way that's more, so if I asked you what's pi factorial, and you have as many ways as you want to try to connect the dots between 3 and 4, then what should you do? Well, it turns out that there's one really standard, famous way to do that. Some of you may have seen, but I'm not at all assuming that everyone has. And that's called the gamma function. So that's what we need to start with. We need the gamma function because we're going to be introducing something called the gamma distribution. We're not done with beta. We were doing beta last time, and hopefully it wasn't too scary, despite being Halloween. We'll come back to the beta. The beta turns out to be extremely closely connected with the gamma. So to understand the beta, we need to do the gamma, which we're about to do. The gamma distribution is named the gamma distribution because it stems from the gamma function, which is one of the most famous functions in all of mathematics. Like if you had a top 10 list, top 10 most famous functions in math, gamma should, I haven't seen anyone make quite a list like that. I've seen people make lists of like the 10 most famous constants, but not the 10 most famous functions. But I'm sure someone has, and if they haven't, or if they have and they did a good job, they would put the gamma function on the list, okay? So it's very, very important in math, not just in probability and statistics, but it's also important in statistics, which is why we need it right now, but it has its own life outside of this subject. All right, so here's the definition of the gamma function. That's just a capital letter gamma of A is defined by the following integral 0 to infinity x to the a e to the minus x dx over x. Usually you'll see it written at the next to the a minus 1 here, which of course is the same thing because you can cancel out one of the x's. But for certain reasons, it's convenient keeping kind of one x on hold over here. It's just a different way to write it, but the same thing. And this is defined for any real a greater than 0. If you try letting a equal 0 here, or if you let a be negative and you think about how this integral is going to behave, it's not going to behave well. It's not going to exist. So for example, if a is 0, this part is gone. We just have e to the minus x over x. And then look at what happens to that near 0, okay? So I'm not going to rewrite the whole thing. Just pretend the x to the a is gone because we let a equal 0. We just have this. Look at what happens when x gets very close to 0. If x is close to 0, e to the minus x is just close to 1, so it's not doing much, right? E to the 0 is 1, so this part's very well behaved. It's just approximately 1, nothing much going on. So what's driving the integral is this 1 over x. The integral of 1 over x is log x. Log of 0 is minus infinity, and that causes major problems. So anyway, but as long as a is greater than 0, this is okay. Same argument. What happens when x is near 0? Well, this e to the minus x doesn't do very much, but here we just have x to the a minus 1, and integrating that is going to be fine. It's going to, you can just do the antiderivative, and you'll see it converges, so it's okay. That's when x goes near 0. It's also you have to consider what happens when it goes to infinity. Well, when x goes to infinity, e to the minus x is the dominant part. This thing, even if a is 1,000,000, then this would be x to the 999,999, completely irrelevant compared to the e to the minus x, which is exponential decay. So that integral is going to converge. So okay, so it exists for any real a greater than 0. This is an extension of the factorial function. It would be a little bit more convenient if gamma of a is a factorial. It turns out that gamma of n is n minus 1 factorial, so you just have to be a little bit careful. That's just for historical reasons, pretty much. This is for for any n a positive integer. So as I said, there's other ways you could extend factorials to the real positive real numbers, but this one turns out to be the one that has at least found the most different applications in math. So this one is the most natural and best one known in a certain sense. So why is this true? Well, let me write down another identity for gamma. Gamma of x plus 1 equals x gamma x. So there's this recursive formula for gamma. You don't need to know much about the gamma function for this course. Depending on what kind of math you do later, you might need a lot of gamma stuff. But for our purposes, you should know the definition. You should know that it extends factorials in this way. You should know this identity. Notice that this is very closely related to this, right? Because let's just look for a second at gamma of 1. We let a equal 1. X's cancel. Integral of e to the minus x. We've seen several times that's just 1. So gamma of 1 equals 1. And then if we plug that in here, it says that gamma of 2, that's 1 plus 1, equals gamma of 2 equals 1 gamma of 1, which is 1. It would be nice if gamma of 2 is 2 factorial, but according to this, gamma of 2 is supposed to be 1 factorial, so that's still correct. Gamma of 2 is 1. And now if we look at gamma of 3, well, we would do 2 plus 1, 2 gamma of 2, and we would get 2, and so on. So notice that this is the same recursive formula that the factorials satisfy. So basically, this formula immediately implies this one, just by, we have the starting point, right? And then they both factorials and gammas satisfy the same recursion, so then they must stay the same for forever. Okay, to prove this thing is just integration by parts, which I'll let you do if you feel like it. Like if you tried to do this integral, just using kind of like the most basic integration by parts from like AP calculus, what you would do is you would not solve the integral, you would not just get an answer for the integral, but what you would get is something that looks exactly like the gamma function again, and you would get this identity just from a straightforward integration by parts. Okay, so that's the gamma function, and that's what happens for factorials. One other thing about the gamma function that's worth knowing is what's gamma of 1/2. Just in case you ever wondered what's the factorial of negative 1/2. And what does that mean? Well, gamma of 1/2, so when it's an integer, we just get factorials, which are integers. Gamma of 1/2 is square root of pi. Kind of a curious looking fact. And where have we seen square roots of pi's before? Normalizing constant from the normal. So we proved that the normalizing constant for the normal is, we have 1 over square root 2 pi, blah, 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 for the normal PDF. So if you let a equal 1/2 here, it doesn't look exactly like the normal, but actually it's similar to what you would get if, if we have this normal, take our normal density, let's say e to the minus x squared over 2 dx. Let's say we're just trying to do that integral, right? And when we did this using the cool trick of writing it down twice, we took the integral we couldn't do, wrote it down a second time, and then we could do it. But if we didn't know that trick, we might say, well, let's make a substitution, For example, I guess the most obvious thing to do might be to let u equal x squared over 2, right? So du equals dx, right? And so, sorry, x dx. So, that would be one thing we could try. This would be a natural thing to try just because it's kind of annoying having this x squared up in the exponent. So if I do this, then at least it's just going to be e to the minus u. That's very nice up in the exponent. But the problem is, we don't actually have, a x here, right? So you can still do this substitution, but what you're going to get is you'll have an x there, and x is essentially square root of u. There's some other constants going on. So you're going to get a square root of u, which is like what you would have here, or you would be dividing by square root of u. So anyway, I'm just saying. You can work through the substitution if you want, but I'm just saying if you do this kind of substitution on the normal integral, you're going to reduce it to something that looks like gamma of 1/2. So you could either think of it as if you knew this fact, this would give you another way to get the normalizing constant of the normal, or the way we actually have it is we already know from a different method the normalizing constant of the normal, then it can prove this fact. So once we have gamma of 1/2, then we know gamma of 3/2. 3/2 is 1 plus 1/2. So if we use this formula, it just says it's 1/2 gamma of 1/2. So that would be square root of pi divided by 2, and so on. So then we could get gamma of 5/2, gamma of 7/2, and get all the half integers that way. All right, so that's just a quick introduction to the gamma function. What's on this board is all you need to know about the gamma function. But now let's talk about the gamma distribution to connect it back to probability. Okay, so here's kind of a simple, naive way to create a PDF based on the gamma function. So we have this integral here. This is just the definition of we didn't prove, that's just the definition of gamma of a. Okay, and suppose we want to somehow guess at some kind of PDF that's going to be related to the gamma function, and we want a valid PDF, and to have a valid PDF, all we need is something that's non-negative and integrates to 1. What would you do? Normalize it. How? How would you normalize this thing? Just divide by that value. So if we divide both sides by gamma of a, that's a PDF. So 1 equals integral 0 to infinity 1 over gamma of a, x to the a, e to the minus x, dx over x. Right? That's what I call just like a simple naive trick that we have that integral, just divide by gamma of a, now we have a PDF. So this thing here is called, everything we're integrating, including this 1 over x. It's easy to forget this 1 over x. You could put it up there as x to the a minus 1, but then it's easy to forget whether that should be a or a minus 1. So I like to write it this way. This is called the gamma of A, comma 1 PDF. There are two parameters. We only see the A right here because the other parameter is 1. The gamma is very closely related to exponential distribution. So the more general one would be gamma of A lambda, and that one would be obtained just by, remember how we got from an exponential 1 to any exponential lambda? It's the exact same idea that we're just putting in a scale. So this is just a scale, or 1 over is a scale. So to get this one, we're just going to make a change of variables. Let's say we wanted y to be gamma of A lambda, and we want to find its PDF. Then we're going to define it as y equals, this is the exact same thing we did for the exponential. We're just going to let y equal x over lambda, where x is we just defined gamma of A1. That's what we just defined as this PDF. And now we want gamma of A lambda. All we're going to do is take a gamma A1, divide by lambda, okay? And so now, at this point, this is just like a really simple transformation, right? Just multiplying by a constant. And, we've been talking about what happens with more complicated transformations, nonlinear stuff and all kinds of complicated transformations. Here we're just multiplying by a constant. So if we want the PDF of y, just to remind you of your change of variables, the PDF of y is fx of x dx dy, right? And in this case, we have y equals x over lambda, which we could, of course, write as x equals lambda y. So dx dy equals lambda. So we just write down the gamma PDF, and we just replace x by x is lambda y. So I'm just replacing x by lambda y to the a e to the minus lambda y, 1 over x, and x is lambda y, times lambda. So that lambda cancels that lambda. And that's what it looks like. I should emphasize the possible values. This is for x greater than 0. This one is for y greater than 0. So this is a like the exponential. The gamma is a continuous distribution on the positive real numbers. Okay. So that's just all right. So that's like a cute trick. Like, how do we get convert this famous function into a distribution? Well, that doesn't really say that that's going to be an important distribution, right? That's sort of like a math trick story, but it's not a probabilistic or statistical story. So I want to show you now how this relates to the gamma distribution. No, the gamma distribution relates to the exponential distribution, okay? That's why we use the letter lambda, and this was analogous to what we did for the exponential. So why does that work out? So for that, we just need a picture. Let's actually relate it to the Poisson also. The gamma relates to the normal distribution we'll see later. It relates to the beta distribution. It relates to the exponential distribution. It relates to the Poisson distribution. And by the way, so we've already discussed all the famous discrete distributions we need in this course. We're almost done with continuous distributions as well. Not done like studying them, but done with like famous ones that you need to know by name. There's a few more, but all of the remaining ones are just variations in some sense of gamma, or possibly with normals. But as you'll see later, gamma is closely related to normal. So once we have the gamma and the normal, we can create the rest of the distributions we'll need. Okay, so all right, so to talk about the gamma and exponential connection, we need to think about a Poisson process. Okay, so we've only talked a little bit about Poisson processes. which is, if you take stat 171, which is stochastic processes, you can do a lot of Poisson process stuff. For our purposes, we just need to know a couple basic facts. First of all, what is a Poisson process? Oh, you've seen them before, but just to quickly remind you, we're imagining emails arriving in an inbox where the number of emails in some time interval, let's say n sub t equals number of emails up to time t. We just have this timeline here. And the Poisson process is called a Poisson process because we're assuming that that's Poisson with rate lambda times t, right? So in a time interval of length t, this is true. I stated this as you're going from 0 to t, but we're actually assuming that this is true in any time interval of length t. It's going to be Poisson lambda t, and there's only one other assumption for a Poisson process. That is that the number of arrivals in disjoint intervals are independent. That is, the number of emails you get from this time to this time is independent of the number of emails you get from this time to this time, for example. So there are only those two assumptions. And okay, so we were a few weeks ago we saw what the connection with the exponential distribution is, and that was before we had even defined the exponential distribution. So I'll remind you of what that was. So we're just drawing draw an X every time you get an email, right? That kind of picture. That's the picture we have in mind. Okay, so what we proved a few weeks ago was that if we call this one T1 is the time of the first email, that's exponential lambda. Okay, and the proof for that is just to say, just to remind you, what's the probability that T1 is greater than T? That's the same thing as saying at time T, I haven't yet gotten any email. That's the same thing as saying that n sub T equals 0, right? Because it's just the same thing, right? No emails up until time T, but that's just given by a Poisson, e to the minus lambda T. The rest of the Poisson stuff, is just 1. So it's just this one-line calculation that shows that, and then you say, oh, that's just 1 minus the exponential lambda CDF, so that's true, okay? So this first time is exponential. Now, using a similar argument, we get that, so that's the time from here to here. Using the same argument repeatedly, the time you have to wait from here from the first email to the second email is also going to be an exponential, and it's independent of the first exponential. Just use the memory list property and think about what, memory list property says, no matter how long you've waited, waiting for this second email, but starting at this point in time is just starting over again. So it's just the same problem again. Same method says that from here to here is another exponential lambda. And from here to here is an exponential lambda, and so on. So all of these times between arrivals are exponential lambda. So our assumption, so that's actually an equivalent way to state the Poisson process. Rather than stating it with Poissons, we could say that the inter-arrival times, that is just these distances between x's in this timeline. Inter-arrival times are IID exponential lambda. So those are the inter-arrival times. But what if we want to know the actual times? So if we call this T2 and T3, T4, T5, and so on, where that's the actual time on the timeline, not just the distance between two times, we want to know that distribution, right? So therefore, we can think of Tn. So let's define Tn to be the time of the nth arrival. nth email, nth phone call, or whatever. We can think of that to get tn, we just add up the first waiting time, then the waiting time from the first to the second, and second to third, and so on. So we can just think of that as the sum of xj, j equals 1 to n, where these xj's are these inter-arrival times, which we just said are exponential lambda IID. Okay. This is the most important story for the gamma distribution, at least for the integer case. Right now I'm assuming n is an integer. Over here, a did not need to be an integer. But if we assume that it is an integer, then this is going to be gamma of n lambda. We haven't shown this yet. So that's something we need to prove, that this kind of a sum of IID exponentials will be gamma. That's what we're going to show next. But you can see the analogy. Remember the negative binomial and the geometric? The geometric, you're waiting for one success in discrete time, right? Negative binomial, you're waiting for however many, 7 successes, say, right? And you can think of the negative binomial as the sum of geometrics. So you wait for your first success, then you wait for your second, and then third, and so on, right, in discrete time. This is the continuous, the exponential is the continuous time analog of the geometric. So this is a continuous time analog of negative binomial. It's how long do you have to wait for n successes in continuous time, where in this case success just means getting an email. So that's a pretty weak definition of success. But anyway, so that's what's going on. Okay, so success is however you wanted to define it. But in this case, we just mean the arrivals. All right, so let's prove this fact now, because just from what I've written, so I'm saying this is true, but just from what I've written here I said add up exponentials, and here I said, write down this PDF with the gamma function, and what does that have to do with that? Not yet clear, right? So we need to check that that's true. Okay. So let's do that. There's 2 ways to do it, at least 2, but there's 2 ways that we know how to do right now. One would be to do a convolution. So that thing over there is just a convolution, right? That you're just adding up. This is a convolution. It's just adding up n IID exponentials. We could do a convolution integral. You could do that for practice. It's not that bad. Actually, stuff will cancel, and it's not bad. And then you could convolve x1 and x2. Then take that thing and convolve it with x3. And then take that thing and convolve it with x4. Well, you get pretty tired of it pretty soon, but hopefully before you got tired of it, you would see a pattern, and you could prove it by induction. But I don't want to do it that way. We have a much better method available. That is MGFs. Okay, MGF, right? Because these are we're adding up IID things, and we know the in class we already derived the MGF of an exponential. It's a nice looking thing, and so we may as well use that. Okay, so that's what we're going to prove right now. So proof that let's say t equals the sum xj, j equals 1 to n with xj IID exponential lambda. Let's do exponential 1 first, is gamma of n1. As long as we can do this when lambda is 1, then we immediately get this for all lambda, because you could just multiply or divide by lambda. Right? Lambda is just a rescaling, and so just scale everything later. It's not really harder to do it with general lambda here. It just makes the notation more cluttered, having all these lambdas floating around everywhere. So I'd rather just set it equal to 1, and then we can always multiply or divide by lambda later. It's not a big deal. All right, so let's do that using the MGF. So the MGF of xj, the MGF of x1, which is since they're IID, they all have the same MGF. It's the same as the MGF of x2 and all xj's, it's just 1 over 1 minus t which we can also think of as a geometric series, right? So we used this before to get all the moments of x1 all at once using the geometric series, and this is valid for t less than 1. Okay? So we did that before. Therefore, we can write down the MGF of t. I'll call it Tn just as a reminder that there's n of them. MGF of Tn, easy. Just raise this to the nth power, right? Because we're adding independent things, multiply the MGF. So just multiply that by itself a bunch of times. We'd have 1 over 1 minus t to the n for t less than 1. Okay? Very little work required to do that. Just put an n there. That's a lot easier than doing a convolution. Well, on the other hand, how do we know that this is the MGF we wanted? Well, to answer that question, we need to look at the MGF of a gamma distribution, right? So now let's consider other problems. I'll make up a new notation just so that I'm not like doing circular reasoning. Well, let's just say y. Let y be gamma of n1, and let's find its MGF. Okay? And we said, before that there's no masquerading distributions that pretend to have a certain MGF and aren't actually what they appear to be, right? So if in fact y has this as its MGF, then we're done, right? So that's what we need to show. So find its MGF. Well, its MGF is the expected value e to the ty equals lotus. I'm just going to write e to the ty, and then I'm going to write down the gamma PDF, which was 1, I'll take out the constant, 1 over gamma of a, y to the a, e to the minus y, and a is n here. So that's gamma of n, y to the n, e to the minus y, dy over y. That's just this thing, and just using lotus, okay? So that's how you can just write down right away. That's why it's lotus. Shouldn't require much thought to write this down. Okay, now it may take some thought. How do we actually do this integral? Well, I guess we can simplify a little bit, collect these two terms. So this is really just 1 over gamma of n, integral 0 to infinity, y to the n, e to the minus, and let's just collect these terms together, 1 minus t times y, dy over y. Because we have e to the minus y and we have e to the ty. Okay? All right, so that may look like a difficult integral, but on the other hand, if you stare at it for a little while, it should start to look familiar. Right? It kind of looks pretty similar to the integrals we've just been doing. I mean, it has some extra constant up here, but this should seem like pretty reminiscent of the gamma function itself, right? So the big, I mean, just in general in this course, it's not really a big deal like how good you are at integration by parts and stuff like that. You'll rarely have to do that. But what you do need to be able to do is pattern recognition and see, well, this looks like a gamma integral. It's just that I have this extra constant in here. That's really no big deal, right? Just make a change of variables just to make this e to the minus x again, right? So we're just going to let x equal 1 minus t y. So that dx equals 1 minus t dy. Okay? So t is less than 1, so that means that this is actually still positive. So the limits of integration So now let's just rewrite that integral. So I'm just making a change of variables just to make that e to the minus x again, because that's going to look more like, it looks very similar to a gamma. Now let's make it extremely similar. That's all I'm doing. So we do 1 over gamma of a. Limits of integration stay 0 to infinity because 0, when y is 0, x is 0, and one goes to infinity, the other goes to infinity. And y to the n is just, well, y is x over 1 minus t, so we are going to get 1 minus t to the minus n. That looks pretty promising, right? Because that's actually exactly what we wanted over there. And then we're going to have x to the n, e to the minus x. One convenient thing about kind of keeping this as dy over y instead of canceling it is that this multiplicative thing is going to cancel. So dy over y is actually the same thing as dx over x. That actually makes this kind of thing easier. And that is, again, gamma of n, not gamma of a, or just let a equal n. So that's why it's handy, dy over y is the same as d over x, just makes it a little bit easier with the algebra. Well, that was exactly the gamma function again, so that's just 1 minus t to the minus n, which is what we wanted. Is the same thing. MGF is the same, so that proves that this statement is true. Okay, so that's nice. That's the connection with the exponential. And well, another thing we need to do is get the moments. So again, that sounds like it could be a nasty problem, but actually it's not bad at all once you see the pattern. Okay, so let's let x be gamma of a1. Oh, and by the way, this calculation here actually in this last line here, and this part, I actually never assumed that n was actually an integer. So this actually shows that this is the correct MGF, even if n could be any positive real number here. So to have the interpretation of the sum of exponentials, then we need an integer. But this is the MGF in general, because that didn't rely on assuming it was an integer. All right, so now let's get some moments. Well, of course we could use the MGF, but actually I think in this case it's even easier just to directly use Lotus. So let's say we want to find expected value of, let's say, x to the c, where I don't even need for c to be an integer. C is just some number. I'm not saying this will exist for all c. We'll have to see whether it exists. Okay, but c is just any constant. In particular, we could let c equal 1 to get the mean, c equals 2 to get the second moment, then we could get the variance, all that. Well, it's just Lotus, so this should be pretty quick. I'm going to write down the, I want, expected value of x to the c, change big X to little x, just Lotus, right? X to the c. And then I'm just going to write down the gamma PDF again, right? So we had 1 over gamma of a, x to the c, and then we had an x to the a, e to the minus x dx over x. Well, okay, obviously we can combine this to be x to the a plus c, 0 infinity x to the a plus c, e to the minus x dx over x. That integral should look very, very familiar again, right? Just pattern recognition. That's x to a power e to the minus x dx over x. That looks very, very much like the gamma function again, right? That is the gamma function. That's just gamma of a plus c over gamma of a. That's just the gamma function. Or if you want, you can multiply and divide by gamma of a plus c and say, oh, we just integrated the gamma a plus c PDF. Must get 1. If it's a PDF, it has to integrate to 1. So, you don't, you don't need to do any like calculus here really. It's just that was just algebra. This times this, and then recognizing that's a gamma, right? So gamma has very, very nice properties in that sense. Beta has some similar nice properties. All right, so that's gamma of A plus C over gamma of A, and our assumption has to be that A plus C is positive, because the gamma function is only defined on positive numbers. If A plus C is less than or equal to 0, then it just doesn't exist. So let's use this just to quickly get the mean. Expected value of x equals, now just let c equal 1. So that's going to be gamma of A plus 1 over gamma of A. But then, remember that identity, gamma of A plus 1 is A gamma A. So this is A gamma A over gamma A, which is just simplifies to A. Very easy looking formula for the mean. And let's check whether this makes sense intuitively. In the case when A is an integer, and we use that interpretation over there, we already knew the answer, right? Because exponential 1 has mean 1. You add up n of them, you have to get mean n by linearity. So we already knew this is correct in the integer case, and this says it's true even if A is not an integer. All right, and let's get the second moment, e of x squared. Well, that's just gamma of A plus 2 over gamma of A. Gamma of A plus 2 is A plus 1 gamma of A. A plus 1 gamma of A plus 1. I'm just using the same thing again, right? Just replace A by A plus 1. So it's A plus 1 gamma of A plus 1. But gamma of A plus 1 is A gamma of A. So again, the gamma of A's cancel. And we would just get A squared plus A. And that tells us the variance. The variance is e of x squared minus e of x squared. So we're subtracting A squared. So that tells us the variance of x also equals A. Again, that's easy to remember. So it says that a gamma A1 has mean A and variance A. Sounds a little like the Poisson, where the mean equals the variance, but this is kind of a special, for the Poisson, the mean is always equal to the variance, and this is kind of just because I let lambda equal 1. So now if we bring back the lambda, gamma of A lambda, well, to get that just, we define that just by rescaling it, by dividing by lambda. So gamma of A lambda has mean A over lambda, but the variance becomes A over lambda squared, because when you when you multiply by a constant, then and you take the variance, then the constant comes out squared. So gamma A lambda has this mean and this variance. But notice that it was just easier to do this thing with lambda equals 1 first, as long as we don't forget at the end to bring back the lambda. All right, so this is just kind of like a introduction to the gamma distribution and the gamma function, how it connects with the exponential. Next time I'll show you how it connects to the beta and the normal. I'll finish a little bit early today because I don't want to scare you again with the beta till next time. See you on Friday.